about that later. Alright, testing 1 2, testing mic 1 2. BGM a bit. Alright, Kon-Kazu minna. I'm your electro student Natsuki Kazuya, who becomes a Vtuber. So tonight will just be just a study stream, and tonight will just be pretty short, not just around like maybe less than an hour maybe. We're just gonna study a few topics about the maths that I've been learning in my academy. So I've been learning a lot about integrals lately. So I think I should start studying from now, because maybe after this I'll be doing my exams. So I think we'll start studying now. And tonight we're going to be studying integrals, and there are 3 topics: double integrals, triple integrals, and also vector fields, if I remember correctly. Yeah, calculus, let's go. Alrighty. So let's see. Open this up. Alright, here we go. So I'll just assume that you guys know about multivariable functions. Like, for example, let me change my eraser to a pencil. Alright. Alright. Oops. Change to eraser. Use that. And go with pencil. Alright, I'll just assume that you guys know about multivariable functions. So there are 2 types. One is the f, x, y, which in this function it actually has 2 variables, x and y. Like, for example, if you do x plus 3y, so this counts as x plus 3y. One variable that includes x and another that includes y. So you can do, if you want to just change into like differentiate x, you can just do fx xy and you'll get 3y. If you do fy xy, there would be, you will only differentiate this part, so you'll get 3. So since if it's fx, whoa, no, sorry about that. This is, wait, let me get my eraser. Hold on. Alright. Sorry about that. Fx, if you differentiate, it will get 1, because you will only differentiate this part. Since this part doesn't have any x, this one will just remain as 0. And this is fy, if you will only differentiate the y, because there's only the y variable in here. So, and then the x has no y variable over here, so this will just be 0. So differentiate respect to x, you'll get 1. Differentiate respect to y, you'll get 3. And then there's the 3 variable functions like f, x, y, and z. So let's see, for example, x squared plus 3y cubed z plus x z squared. So yeah, we'll just add a power at the top of these variables so that you guys get clearer understanding. This is just to recall what I've learned back in the academy. So fx, y, z, differentiate only the x, you'll get 2x. So this one, so if it's fx, this one will be, there's no x here, will be 0 plus 0, differentiate the x, you'll get z squared. So we'll be left with 2x plus z squared. As for fy, there will be no y on the first variable, so this will be 0 plus, so there's a y here, we'll differentiate that, it will be 9y squared z. There's no y in the third one, so this one will just be 0. And lastly, if you want to do fz, for example, this will just be 0 plus 3y cubed plus 2xz. So that is just the basic partial derivatives that we're going to use for tonight. So let's see, got my eraser, take this out. Oops. This is just gonna be a pain in the ass to do this. So come on. Alright, there we go. So we get a pencil. So the first thing that we're gonna study for tonight is double integrals. So double integrals. So double integrals. What are double integrals? It's basically, they're kind of like the integrals that you've learned before. And usually it's, what was the first one again? Definite integrals from a to b, fx, dy. That is the basic integral that we've learned. But if you want to learn about double integrals, you need to understand something called the Riemann sum. So the Riemann sum, you make a sum here, and if I check my textbook again, hold on a sec. Where was the Riemann sum again? Alright, found it. So we define as the volume of, should take this out. Hold on. There are just so many things scuffed here, sorry about that. So take this out. Hold on. Excuse me, sorry about that. Okay, so v from the limit to, what was that again? The derivative p approaching 0, the summation of n, where was it again? L equals to 1. Then f, my goodness, I can't remember this. Okay, so ui, vi, So it's an I, delta AI. So since we've learned this is what they call the Riemann Sum. So if you want to, this one will it will be related to the Riemann Sum. So if you try to make some sort of region here with a function, let's just say this is f u i v i, and then there will be these parts where you have to do something like this. Like you have to integrate this one by one and add all of them together until you get until infinity as it is. So that means you'll get the area at the bottom of this curve. So just release this. Oops. All right. So if you want to use the double integral, we need to make some sort of a range. So the range between between a region. So like for example, if you make a curve here, there's a graph. Here is a straight line. Let's label this y equals to x, and we'll put here a region. Alright, so y equals to x, and then let's say 0 equals to 4. So if you want to define the region, it will be r, make a curly bracket, and then hold on, where is it again? Region. Really, I'm forgetting a lot of stuff now. Sorry. Hold on. Oh, there you are. So the region of a point at x, y, start from, if we want to do a region, if we want to start a region with x first, so x would be from 0 to 4, while y, so this will be the x region, and this one will be x from 0 to 4. This one will be 0 from y to x. Okay, why is it the region is like this? Because if you want to do an integral, for example, integral of r f x y dA, dA equals to, you have to make both limits with x and y. So from 0 to 4, and then make another integral 0 to x, and then we'll make an fxy, but this time, since we've already put the limits inside the integrals, so we'll use the range if it's from 0 to x. If you want to integrate that means this will be in terms of y, so dy, and then integrate from 0 to 4, so this will be dx. So how does this work actually? So this thing, the integral works by integrating this part first, and then you integrate the other part. That's how the double integrals work. It's basically like if you integrate, you integrate twice. So with like if you have two variables, you have to integrate them. You have to integrate both of them. So if there's xy here, you'll integrate with dy and dx. So hold on, let me erase that. Where's that? Alright. So let's try and find the exercise from the textbook I'm using right now. Oh yeah, by the way, sorry about that. Forgot that the fx just now. So we'll say that R is xy region. This is a curly bracket. A x b then c y d. Integrate a b c d f, the multivariable fxy. So this is dc. We'll take this. So since this is the range of y, we'll put dy. This is the range of x, we'll put in dx. So this is actually known as Fubini's theorem, which is the theorem where from the region just now you set up the limits between inside one region in an enclosed region, and then you set the range of x and the range of y. I think that's it for the Fubini's theorem. I mean, because Fubini's theorem, the base it's based on this R f x y dA. So you can change this using the regions given, and then convert into this Fubini's theorem. So anyone got that? I hope so. Alrighty, so hold on. Alright, what's next on the list? So let's just make one question. Let's just find one question here, and we'll do an example. Alrighty. So we'll do the question. Integrate R for x for e to the power of x squared for exponent minus 5 sine y dA. And then the region given for both terms x and y would be, it was given yx y equal to 0, x equal to 4. So if we try and construct a graph, which is a region, so the curve is y equals to x up here, x, y, we'll set up a region here. Sorry if it's a bit slanted. So from 0 to 4. Now we have that y is equal to 0, and x equals to 4. So if you do this, y equal to 0, x would also be equal to 0. So if we try to make the region from the x part from 0 to 4. So the region from the region of x, 0, x from x from 0 to 4. Well, they also do a y from 0 up until this curve, this straight line, y equals to x. So we'll do y equals to x. Alright. So since it's starting y equals to 0, from 0 until y up until x. That means, for example, this is a line of x equals to 4, so it will be approaching starting from the origin to 4. But if it's y, you have to start from 0, since y starts from 0, up until the curve itself. The straight line, I mean. So that's how you set up the intervals. So if you use Fubini's theorem, it would be from 0 to 4. We'll start with x, and then from 0 to x. So 4 exponential to the power of x squared minus 5 sine y. So since this dA will be replacing with the intervals that we've set. So for example, since this is from 0 to x, we'll take this. So this one we will integrate dy first, and then from 0 to 4 we will integrate with respect to x. So from here we can just we can integrate as per normal. So like for example, like this, 0 to 4, 4y exponential to the power of x squared minus, since this is sine y, I can't remember the integration of sine. Hold on, d over dx sine y, no wait, d over dy sine y, cosine y, d over dy cosine y would be minus sine y. So this is minus sine. So if we integrate it, it will become plus 5 cosine y, reaching from 0 to x. And this will also be dx. So we've integrated the y's. So this will become from 0 to 4, 4x exponential to the power of x squared plus 5 cosine x dx. So 0, if we do if we do this, oh yeah, now I remember. So hold on. So if we do 0 minus, so y equal to 0 over here. We'll do this. We'll do this. So this will be 0 minus, so 5 cosine 0. So cosine 0 is 1. So 1 times 5 will be 5, and dx. So once we got this, we'll just erase this. Oops, a bit too big. So we'll get minus 5 dx. So now if we try and integrate one more time. Hold on. We'll go up here. Now we'll start to integrate 4x to the power 4x exponential to the power of ex squared. Let me see. 4e power of x squared. Okay, so if you remember correctly, we'll go back here. We'll just go back here. Alright. So for example, if you integrate from e to the power exponent to the power of x squared, differentiate that, or integrate, it should be 1 over, no wait, oh, alright, so differentiate e to the power of x squared. Is it differentiate or integrate? I think it's different. I think it's integrate. So we'll just do an antiderivative. Antiderivative would be 1 over 2. 1 over 2x squared, if I remember correctly. Or maybe we'll just take the example from. We'll take the example here, evaluating integral 2 exponent to the power of x squared. Plus integrate the cosine. So integrating cost will be 5 sine x minus 5x. So x approaching 0 to 4. So now if we just add these values here, 4x, sine x, and 5x, so it would be 2e to the power of 16 minus 20. So we'll take this out, 2 to the power of e to exponent power 16 minus 10. And that will be our answer. I think so. But wait, hold on. Wait, that's not the answer, sorry. Try that again. Alright, so plus 5 sine 4 minus 20. So if you put 0, and then put 0, and put another 0 here, you will only get, so you'll have to minus the thing, minus the function. Then you'll get, so this is 0, this one would be 1, right, it's 1 and 2. So this one would be, I'm just too lazy to erase now, haha, sorry. So we'll get 22. Alrighty. Now what? Now, I think that's all you guys have to know about integrals. So let me see. What's next on the list? Maybe we'll try and do another example. So another example on the textbook. Do this, pencil again. Then, so let's just make the regions y equals to the square root of x would be equal to 0 and y would be equals to 3. So if you make a region, so y would be equals to square root x, be like this. So that why is it like this? This is x. This should be. This is x squared. This is x squared. But then, if we flip it like this, this would be y squared. So the y has to be singled out. So we'll just do a square root. So this one would be square root x. So yeah, I hope you guys could actually understand this, because even I can't remember what I'm doing right now. So the regions are 0, and then this is the region from x equal to 0 and y equals to 3. So I forgot to put this. Oops, not 4. It's y. So we'll make a small region here. So the region would be over here. So this will be our r, and then our region would be x equal to 0, y equals to 3. So since our x is like this, x will start from 0. So x will be from here to the curve. So x would be from 0 to y squared. Why? Because since we do y equals to square root x, but this time we're letting add x as the term. We'll square this, do y squared equals to x. So this would be the curve x 0 from 0 to y squared. And then if you do something like y, it will be approaching from 0 up until 3. That means it will go up until up here. That is how trying to set the region actually works. So now the question given is that we have to evaluate the region of 2xy plus 2xy squared 2y cosine x dA. So next, 0xy squared 0y3. So we'll start with dy at the back. So we'll start first. Y will start first from 0 to 3, and then from 0 to y squared 2xy squared plus 2y cosine x. Excuse me, sorry about that. 2xy squared plus 2y cosine x, 0y squared. So So this one is this is the region of x right here. So it will be dx and dy. So this will be converted to Fubini's theorem. So next, what we should do is we'll start integrating. So 0 to 3. Whoops. So integrate x squared y squared, because if you integrate this, square and over 2. So you'll just cancel out 2. Y squared, and then cosine. Integrate cosine just now was sine x. So 2y sine x. Approaching 0, 2y squared. And then there's dy. Alright, and then we'll start evaluating this part here, the limits. So from 0 to 3, it would be from y squared, so y squared, a dot in the middle, plus 2y sine y squared. Well, that's true, isn't it? Yeah, it is true. So if there is a 0 minus, this would be 0 minus, and then sine x 0, we'll put in 0 inside sine x, so it will be 0. And then we'll put dy at the back. So now we'll just try and evaluate all of this first. Integral from 0 to 3, oops, not y3, y4 plus 2y sine y squared dy. And then we'll integrate, and then we'll finally integrate this y5 over 5. And then what about the next one? Wait, is this 6? Wait. Hold on. Oh, right. This should be y squared. So this would be y power 6. So my 2 doesn't look like a 2. So we'll do 2 here, we'll do 2 here. We'll do another 2 here. So y squared, and then another squared. So y2 times 2, it would be 4. And then 4 plus 2. So it multiplies with y squared here. So it would be, eraser again. Oops. Reduce a bit of the size. Okay, pencil. Y power 6 plus 2y sine y squared dy. So this one would be y power 7 over 7 plus if we try and differentiate cosine y squared, for example, try and differentiate this would be 2y, no. Hold on a sec. Differentiate cosine would be minus sine y squared 2y. So if you differentiate that, minus sine y squared would be equals to the derivative 1 over 2y times the derivative of cosine y squared. Nah, you don't really need to put the derivative. I mean, let's just imagine if we... okay. Cosine y squared. God, my handwriting is terrible. Sorry about that. Yeah, we put the minus sign here as well. Alright, so minus, this one would be minus, what was that again? 1 over, since this is 2y, so we'll just cancel this, we'll just take this out. Yeah, we'll just cross it out like that. So minus cosine y squared from 0 to 3. So we'll get 3 to the power of 7 over 7 minus cosine 9. And that will be our answer. I will try to approximate it. Calculator. 7 minus cosine 9. Radian equals to. Wait, should it be radians or degrees? I will put it degrees. No, wait, we have to do radians. Alright. B equals to 313.34. And that would be the answer now. Let's get our eraser and we'll do this again. My goodness, it's already 45 minutes. I am pretty slow. Sorry about that. Alright, pencil. We got a pencil. No, I think we'll just go straight into triple integrals. First the triple integrals. Alright. So for example, if you have a 3-point graph. Hold on. Let's try that again. That was this and like this. So if you use the right hand thumb rule. So right hand thumb rule, the x direction would be from your hands. No wait. The direction of your fingers, and then the y would be at the direction of your, what do you call that again? Your arms, I think. Well, the z would be at the direction of your thumb. So it should be x, y, z. And then we'll put just some random 3D shape here. Like this. We'll do it like this, and this, and this. Do it like that, and like that. So let this entire volume be Q. And if you use the Riemann Sum again, it would be from not I, but Ni would be equals to 1. So F X, no, not XY, but UI, VI, WI, and this one would be delta VI. delta vi. So delta vi, and then the region of this, the region bounded by this Q over here would be Q using a curly bracket. What was that again? X, Y, Z. With this, and then the region would be bounded by A to, oops, wrong symbol. So X would be from A to B, Y would be from C to D, and then there's this Z direction. So let's just say we'll do approaching, so Z approaching from M to N. So that is the region bounded by Q. So if you want to express this in the form of an integral, we use triple integrals. So like the double integral just now, we're not actually integrating it twice, not twice, but we're actually going to integrate this 3 times. So before that, let me just take a sip of my water. Oops. Hold up. Whoa, what just happened there? Oh, right. Sorry about that. Oops. Just a sec. Alright. So, where were we? For example, if you want to do, since there are 3 regions, we have to use the Fubini's theorem again. Fubini's theorem can be applied in double integral and triple integral. This time instead, we'll do 3 integrals. So now we have to deal with 3 of them instead of R just now, since there's only one plane. Now we're going to use Q, F, X, Y, and Z, dV. So this would be, if we use the Fubini's theorem, it would be we'll start with X first, A to B, C to D, and then M to N. Then we'll do F, X, Y, Z. So N and M. N and M first, from M to N, dz, and then C to D. So it would be dy. And then next would be dx. So dz, dy, dx. dy is from C to D, and dx is from A to B. Alright, so now that we got the gist of it, let's try and find something. So, a pretty popular question that has been asked in triple integrals would be like, take this, oops, take that out, sorry for that, all the time. Alright, change back to our pencil, and then we will make a region. So if you guys have heard of the tetrahedron, we'll just we'll make this x, y, z. So it's tetrahedron is like a pyramid, but the bottom face of it is actually a triangle. If you remember a pyramid is actually like a square, but tetrahedron, the bottom face is actually a triangle. So you can just construct this since we have three planes: xz, zy, and xy. So let's just say that we make a line from x to z. Imagine if we have like some sort of equation that connects these two together in the xz plane. Do one, and then we'll make another line, construct here z to y, and we'll make another one from x to y. And we have a tetrahedron. So it's kind of like these lines here, these lines connect as a triangle if we look at it like this in just one perspective. But if you look at it, there will be a region at back here, region at back here, and a region at back here, as well as the region in front of all of these three. This is kind of the base, actually, the base of the tetrahedron. So from that, let's try that question. So we'll set a region here. Let's just imagine that x is 2, y would be 4, and z equals to 4. So this region will be starting from oops. Ooh, what's going on? Alright. Starting from here to the plane at the front, you know. That means like the plane that we are looking right now, not the ones at the back at the plane zy, xy, and xz. So the plane like the one up top here. So this one would be not z. Sorry about that. 2x plus y plus z equals to 4. So that will be the region at the highest point. So now, how should we actually solve this, you know? How should we solve this? Oh, and the question itself, where was it again? We have to integrate this 1, 2, 3, 6, x, y, dv, q. Alright, 6xy dv. So now, since we have the tetrahedron here, let's just say that we try to take out one plane, the ones that I shaded around here. These are the regions at each plane. Like for example, x, y. So let's just take this x to y, this 2 to 4. So this will be our r. Let me check the question. Let me check the example again. All right. Oopsie. 0, 1 over 2, x squared y. Okay. So we'll just make a curve. So when z equals to 0, y would be equals to 4 minus 2x. So we'll make a region here, and let's just say that we're just using y as the subject. So Z will do it later. So we'll just focus on X and Y. So we'll start here. X from 0 to 2. X is the region from 0 to 2. And then the Y is from 0 Y 4 minus 2x. Alright, so that will be inside the x and y plane. But then we have the z. So the z region would be, if we let the z as subject, z would be equals to 4 minus 2x minus y. So we'll start from the region here up until the plane at the front here. So plane at the front here behind in front of these planes. So 0 z from approaching from 0 to 4 minus 2x minus y. So let's just erase this, take this out. Is it really that small? Is it really that small? Maybe not. I think it's fine. As long as people can see my handwriting now. So okay. So this is the original integral that we're going to use, but this time we'll do something called we'll do the Fubini's theorem again. So Fubini's theorem, we'll start with z first. We'll start with the easiest one at the last, which is basically we're doing the first. I don't know which one. Okay, so from 0 to 2, from 0 to 4 minus 2x, and another one from 0 to 4 minus 2x minus y. And then the function is 6xy. So this is the region, the interval of z. So it would be dz. This is the region of y. It would be dy. This would be the region of x, and this would be dx. So now we'll try and integrate this one by one. So 0 to 2, 0 to 4 minus 2x. So we integrate this. Since there's no z here, we'll add it. We'll just add a z in there. 6xy, 6xy, z. So integrate from 0 to 4 minus 2x minus y. dy, it remains dy and dx. I can't believe it's already 10. So basically I've been slacking off. Sorry about that. So 0 to 2, 0 to 4 minus 2x. 6xy. 4 minus 2x minus y. dy dx. So since there's 0, so we'll just put this minus 0 just for you guys. It makes things easier to understand. So 6xy. Interval from 0 to 2, interval 0 to 4 minus 2x. 6xy, 4x to y, so 6 times 4 would be 24xy minus 12x square y. I'm missing a lot of space here, sorry about that. And my 12x square y minus 6xy squared. Oh dear, I'm losing face. So dy dx. Okay. So we'll just put this above right here. Go up. Go up. Even I can see my handwriting right now. Haha. Alright. 0. No, not 6. 0 to 2. 24xy, since we're using dy. Sorry about that. Alright. dy would be, so 24xy integrate with respect to dy would be 12xy squared minus 6x squared y squared minus 2xy cubed. Alright. So integrate from 0 to 4 minus 2x dx. We'll get my eraser. This. Wait, hold on. What just happened? Try that again. I'm using Sketch.io, by the way. This is not really a place, not really a whiteboard for you to draw. Oops, not this one. Not really a whiteboard for you to actually draw this, to actually do equations, but it's better than nothing. I actually wanted to try using Krita, but for some reason it can't be connected to Streamlabs. Don't know why. So we'll go up here. So 0, let's see, from 0 to 2, oops, 12. So this is with respect to y. 4 minus 2x squared. It doesn't look like 2 here. Minus 6x squared. 4 minus 2x squared. Oops. And then where was it again? 2x minus 4 minus 2x cubed. And this would be dx. So there's 0, 0, 0. So we'll just go all with minus 0. Alrighty, so I think this integral is going to be pretty difficult to actually integrate. It will take a pretty long time, probably the whole paper as well. So let's just skip this. But I think you guys would actually get the gist of it, because since it's only one variable, which is x. So if you manage to expand this, the 4 minus 2x bracket squared and 4 minus 2x cubed. So if you manage to integrate this, it'll just make you can just integrate like a normal first single integral. So this will just be like integrate with respect to dx. So yeah, that's how you do it. No, not again. You take the eraser out. So there's a lot more towards double integrals and triple integrals that I haven't covered yet. But yeah, I mean, I did say I wanted to do this within an hour, but nah, I think I'll just throw it in for you guys as well. So, like, okay, double integral. My latency is really slow. Not my latency, it's lagging for some reason. OUBLE double triple. So double and triple. So this double integral, you can actually have the rectangular coordinates. Rectangular would be dx dy. My sketchpad is actually lagging. I wonder why. Rectangular, and we also have the polar. This is the rectangular coordinates, by the way. Like, for example, if you do x, y, but polar would be r and theta. But then again, you have to put r, dr, d theta. These two coordinates you can interchange, and for rectangular it's easy because if you have a function like I don't know, maybe a quadratic function x square, you can use the rectangular components. But if polar, let's just say if you have a circle. This is not a circle, it's actually an oval, or whatever it is. Sorry about that. So, with that, all inside the circle, let's just say it is a circle. So there will be a radius here. So the radius will be from 0 to r, and then since it's just moving in one circle, it will be from 0 theta and up until 2 pi. So that's how it works. This is for polar coordinates. Well, and then from the rectangular and polar coordinates, it will be the same for triple integrals. But so, for example, if you do r and p, it's just the same thing, x, y, but you also have z. So it will be dx, dy, dz. And then there's polar, would be r theta z, or no, it's not polar coordinates. It's not actually called polar coordinates here. Let me correct that again. I mean, technically it's polar coordinates, but the coordinates don't actually form a circle. It kind of actually forms a cylinder. So with pencil. So like if a rectangle, no, not like that. 1, 2, 3. Then we'll do the tetrahedron again, and over here. So this one would be x, this one would be y, this one would be z. Alright, that would be z. That will be rectangular coordinates. But cylindrical coordinates, you still have the polar coordinates. So we'll make a circle down here. Circle doesn't work again. Alright, circle here. Circle up here. And form 2 point. points here. That's not straight. Let's try that again. That's still not straight. Sorry about that. Okay, so this is a cylinder. So the coordinates here, it's still like polar, but you have a z up top. So we call this cylindrical coordinates. Cylinder, cylindrical. So it would be r theta z. Yeah, r theta z. But I mean, it doesn't. I mean, from coordinates it does matter, but for the integral it really doesn't though. So r dr d theta dz. So it's just the same thing with polar coordinates, but you just add a dz at the back. So yeah, that is the cylindrical coordinates. But in triple integrals, there's actually another one, another coordinate system called, if we do this again, but this time it's a full circle. This is not a circle, since this is a 3D diagram. It is actually a sphere. So a sphere. So a sphere has its own coordinate system as well. So we call this as spherical. Spherical. Alright. Spherical coordinates. So there will be. So the coordinates would be rho. My rho is terrible. It would be rho. What was that again? Phi. And then there would be theta. That's not a theta. It's 0. Alright. Now to rho squared. Sine, psi, d rho, that's not d psi, oops, d psi, theta. That will be used for spherical coordinates. So the spherical coordinates, the domain. For polar coordinates, the domain of theta would be from 0 theta to pi. My goodness, that doesn't look like 2 pi at all. Alright, so 2 pi. And then the spherical would be pi. Wait. So the phi, from 0 to pi. That is for the spherical coordinates only. Because spherical coordinates, since the circle formed at the bottom, well, there's also another coordinate from starting from the z-axis. So here you'll make an angle, and then you'll make a line here. And this would be rho. It's not rho, but yeah. So it's just an angle from the z-axis, starting from 0 up until the bottom here. That is why it's actually up until pi. So you don't really have it's not towards a full circle. I mean, because we already have a full circle at the theta there. So we just need pi from here to here. So I guess that's all for the integrals. So give me a sec. Alright. Now for pencil. Alright. So now we've covered both the double integral and the triple integral. So we could talk on. I'll just talk briefly on the vector fields. So let's see. My goodness, my handwriting. V, E, C, T, O R F I E. I'll just touch on this a bit, just pretty short. So vector field F, for example, from this would be, let's just say this is F1, F2, F3. Either it has only X and Y or X, Y, Z. So vector field, if there's a lot of things you need to know about the vector field. Like for example, there is the curl, there is the gradient field. We'll touch on gradient field first before curl, and then we also have the diverge. My goodness, it's so hard to write in this sketchpad right now. God damn it. So, alright, what's next? Alright, so we'll start with gradient field. So we'll just touch on this a bit briefly. So if you want to do like a gradient field, we'll just have to do fx. It's not good. Fx, fy, fz. So that will be the gradient field. But if you want to talk about the curl is going to be pretty long. But if you want to simplify it, let's just say that this is actually a determinant. So this is I, this is J, this is K. Alright, is it F1? Yes, it is F1. So F1, no, not F, this, delta X. You can't actually like exchange this like d over dx at J or K. It has to remain like that. So J, F2, no, that's not good. Delta, not delta, d over dy, and no, not J, but K. F3, d over dz. So now we'll just use a determinant system. Plus minus plus. We'll do from here to here, and then J here, while K would be like that. And then that is how you do a curl. Like this is the determinant method, by the way. So I think I'll try and change it. No, I didn't think we should. So this one would be plus this multiplied with this minus the ones of F3 multiplied by d over dy, d over dy. That is curl. And also remember, curl is actually a vector, because there's another term called the divergence, or simply put div, the divergence of f. So divergence of f is actually the dot product. So if you do like f1, f2, and f3, then we'll put in d dx, d dy, d this. So now we'll do something called the dot product. That means we have to add three terms together. D f1 over dx d f2 over dy d f3 over dz. And remember that divergence is actually a scalar. And that is all. I mean, I'm really sorry about the dragging just now, from the double integral, because I didn't find good questions just now. But yeah, at least we managed to finish the topics today. So guys, I think I'll end it here. Let me erase this. So okay, a little hold on, let me erase this. Where is it? Alright, so a little PSA here. I'm actually going to take a hiatus for now, because I will actually be taking on my finals in 2 weeks from now, and I'll also be attending some voice acting class so that I can improve my voice acting, because my voice right now, because I'm talking, I'm literally close to a freaking sore throat. So I'm really sorry about that. I'll try and get my voice back, and I'll try and return as much as possible, as quickly as possible after I finish my exams. And I'll try and make a lot more content, because after that it will be a mid-semester break for 3 months, and I'll try and put in a bit of a feed for you guys to answer, like what content should I make, and all that. And I'm gonna be approaching my birthday on 27th of June. So yeah, be sure to anticipate it soon. So so I think that's all from me today. Not today, it's 10:25 p.m. right now. So guys, Natsuki Kazuya. So if you guys enjoy the content I make, please like and share it with your friends and family, and subscribe. And I'll see you in the next